Let's continue with the book, guys, everyone, from page 26 or 34. All these are codes. I'm gonna figure it out as soon as possible, but not right now. Okay, here we go. Main and getLine communicate both through a pair of arguments and a returned value. What now? In getLine, the arguments are declared by the lines, which specifies that the first argument is an array, and the second is an integer. The length of the array S is not specified in getLine since it is determined in main. getLine uses return to send a value back to the caller, just as the function power did. Some functions return a useful value. Others, like copy, are only used for their effect and return no value. getLine puts the character \0, the null character, whose value is 0. At the end of the array, it is creating to mark the end of the string of characters. This convention is also used by the C compiler. When a string constant like hello \n is written in a C program, the compiler creates an array of characters containing the characters of the string and terminates it with the \0 so that functions such as printf can detect the end. What happened? What's going on? The %s format specification in printf expects the %s format specification in printf expects a string represented in this form. If you examine copy, you will discover that it too relies on the fact that its input argument S1 is terminated by \0, and it copies this character onto the output argument S2. All of this implies that \0 is not a part of normal text. It is worthy mentioning in passing that even a program as small as this one presents some sticky design problems. For example, what should main do if it encounters a line which is bigger than its limit? getLine works properly in that it stops collecting when the array is full, even if no new line has been seen. By testing the length and the last character returned, main can determine whether the line was too long, and then cope as it wishes. In the interest of brevity, we have ignored the issue. There is no way for a user of getLine to know in advance how long an input line might be, so getLine checks for overflow. On the other hand, the user of copy already knows or can find out how big the strings are. So we have chosen not to add error checking to it. Exercise 1 middle score 14. Revise the main routine of the longest line program so it will correctly print the length of arbitrarily long input lines and as much as possible of the text. Exercise 1 middle score 15. Write a program to print all lines that are longer than 80 characters. Exercise 1 middle score 16. Write a program to remove trailing blanks and tabs from each line of input and to delete entirely blank lines. Exercise 1 middle score 17. Write a function which reverses the character string S. Use it to write a program which reverses its input a line at a time. Scope external variables. The variables in main, line, save, etc. are private or local to main. Because they are declared within main, no other function can have direct access to them. The same is true of the variables in other functions. For example, the variable I in getLine is unrelated to the I in copy. Each local variable in a routine comes into existence only when the function is called, and disappears when the function is excited. It is for this reason that such variables are usually known as automatic variables. Following terminology in other languages, we will use the term automatic henceforth to refer to these dynamic local variables. Chapter 4 discusses the static storage class, in which local variables do retain their values between function invocations. Because automatic variables come and go with function invocation, they do not retain their values from one call to the next. It must be explicitly set upon each entry. If they are not set, they will contain garbage. As an alternative to automatic variables, it is possible to define variables which are external to all functions, that is, global variables which can be accessed by name by any function that cares to. This mechanism is rather like Fortran common or PL/I external, because external variables are globally accessible. They can be used instead of argument lists to communicate data between functions. Furthermore, because external variables remain in existence permanently, rather than appearing and disappearing as functions are called and excited, they retain their values even after the functions that set them are done. An external variable has to be defined outside of any function. This allocates actual storage for it. The variable must also be declared in each function that wants to access it. This may be done either by an explicit external declaration or implicitly by context. To make the discussion concrete, let us rewrite the longest line program with line, save, and max as external variables. This requires changing the calls, declarations, and bodies of all three functions. Like these words. Okay, so many whole page. Here. The external variables in main, getLine, and copy are defined by the first lines of the example above, which state their type and cause storage to be allocated for them. Syntactically, external definitions are just like the declarations we have used previously. But since they occur outside of functions, the variables are external. Before a function can use an external variable, the name of the variable must be made known to the function. One way to do this is to write an external declaration in the function. The declaration is the same as before except for the added keyword external. In certain circumstances, the external declaration can be emptied. If the external definition of a variable occurs in the source file before it's used in a particular function, then there is no need for an external declaration in the function. The external declarations in main, getLine, and copy are thus redundant. In fact, common practice is to place definitions of all external variables at the beginning of the source file, and then omit all external declarations. If the program is on several source files, and a variable is defined in, say, F1 is used in F2, then an external declaration is needed in file 2 to connect the two occurrences of the variable. This topic is discussed at length in Chapter 4. You should note that we are using the words declaration and definition carefully when we refer to external variables in this section. Definition refers to the place where the variable is actually created or assigned storage. Declaration refers to places where the nature of the variable is stated but no storage is allocated. By the way, there is a tendency to make everything inside an external variable because it appears to simplify communications. Argument lists are short and variables are always there when you want them, but external variables are always there even when you don't want them. This style of coding is fraught with peril since it leads to programs whose data connections are not at all obvious. Variables can be changed in unexpected and even inadvertent ways, and the program is hard to modify if it becomes necessary. The second version of the longest line program is inferior to the first, partly for these reasons and partly because it destroys the generality of two quite useful functions by writing into them the names of the variables they will manipulate. Exercise 1 middle score 18. The test in the fourth statement of getLine above is rather ungainly. Rewrite the program to make it clearer, but retain the same behavior at end of file or buffer overflow. Is this behavior the most reasonable? 1.11 Summary. At this point, we have covered what might be called the conventional core of C. With this handful of building blocks, it's possible to write useful programs of considerable size. And it would probably be a good idea if you paused long enough to do so. The exercises that follow are intended to give you suggestions for programs of somewhat greater complexity than the ones presented in this chapter. After you have this much of C under control, it will be well worth your effort to read on. For the features covered in the next few chapters are where the power and expressiveness and expressiveness of the language begin to become apparent. Exercise 1 minute score 19. Write a program D tab which replaces tabs in the input with the proper number of blanks to space to the next tab stop. Assume a fixed set of tab stops, say every n positions. Exercise 1 minute score 20. Write the program in tab which replaces string of blanks by the minimum number of tabs and blanks to achieve the same spacing. Use the same tab stops as for D tab. Exercise 1 minute score 21. Write a program to fold long input lines after the last non-blank character that occurs before the nth column of input, where n is a parameter. Make sure your program does something intelligent with very long lines. And if there are no blanks or tabs before the specified column. Exercise 1 minute score 22. Write a program to remove all comments from a C program. Don't forget to handle quoted strings and character constants properly. Exercise 1 minute score 23. Write a program to check a C program for rudimentary syntax errors like unbalanced parentheses, breaches, or braces. Don't forget about quotes, both single and double, and comments. This program is hard if you do it in full generality. Okay. Chapter 2. Types, operators, and expressions. Variables and constants are the basic data objects manipulated in a program. Declarations list the variables to be used and state what type they have and perhaps what their initial values are. Operators specify what is to be done to them. Expressions combine variables and constants to produce new values. These are the topics of this chapter. Hang on. 2.1 Variable names. Although we didn't come right out and say so, there are some restrictions on variable and symbolic constant names. Names are made up of letters and digits. The first character must be a letter. The underscore counts as a letter. It is useful for improving the readability of long variable names. Upper and lowercase are different. Traditional C practice is to use lowercase for variable names and all uppercase for symbolic constants. Only the first 8 characters of an internal name are significant, although more may be used for external names such as function names and external variables. The number may be less than 8. Because external names are used by various assemblers and loaders. Appendix A lists details. Furthermore, keywords like if, else, in, float, etc. are reserved. You can't use them as variable names. They must be in lowercase. Naturally, it is wise to choose variable names that mean something, that are related to the purpose of the variable, and that are unlikely to get mixed up typographically. 2.2 Data types and sizes. There are only a few basic data types in C. Char, int, float, double. In addition, there are a number of qualifiers which can be applied to ints, short, long, and unsigned. Short and long refer to different sizes of integers. Unsigned numbers obey the laws of arithmetic modulo 2 power n, where n is the number of bits in an int. Unsigned numbers are always positive. The declarations for the qualifiers look like this. The word int can be emptied in such situations, and typically is the precision of these objects depends on the machine at hand. Table below shows some representative values. The intent is that short and long should provide different lengths of integers where practical. Int will normally reflect the most natural size for a particular machine. As you can see, each compiler is free to interpret short and long as appropriate for its own hardware. About all you should count on is that short is no longer than long. 2.3 Constants, int and float constants have already been disposed of, except to note that the usual, like this or this, scientific notation for floats is also legal. Every floating point constant is taken to be double, so the lowercase e notation serves for both float and double. Long constants are written in the style 1, 2, 3, uppercase L. An ordinary integer constant that is too long to fit in an int is also taken to be a long. There is a notation for octal and hexadecimal constants. A leading 0 on an int constant implies octal. A leading 0x or 0x indicates hexadecimal. For example, decimal 31 can be written as 037 in octal and 0x1f or 0x1f in hex. Hexadecimal and octal constants may also be followed by L to make them long. A character constant is a single character written within single quotes. As in single quote x, the value of a character constant is the numeric value of the character in the machine's character set. For example, in the ASCII character set, the character 0 or single quote 0 is 48, and in ASCII single quote 0 is 240. Both quite different from the numeric value 0. Writing single quote 0 instead of a numeric value like 48 or 240 makes the program independent of the particular value. Character constants participate in numeric operations just as any other numbers, although they are most often used in comparisons with the other characters. A later section treats conversion rules. Certain non-graphic characters can be represented in character constants by escape sequences like \n, \t, \0, single quote, etc., which look like two characters but are actually only one. In addition, an arbitrary byte-sized bit pattern can be generated by writing, where DDD is 1, 2, 3 octal digits, is in like this. The character constant single quote \0 represents the character with value 0. Single quote \0 is often written instead of 0 to emphasize the character nature of some expression. A constant expression is an expression that involves only constants. Such expressions are evaluated at compile time rather than runtime, and accordingly may be used in any place that a constant may be, as in, or a string constant is a sequence of 0 or more characters surrounded by double quotes, as in, like this. The quotes are not part of the string but serve only to delimit it. The same escape sequences used for character constants apply in strings. Double quote represents the double quote character. Technically, a string is an array whose elements are single characters. The compiler automatically places a null character \0 at the end of each such string, so programs can confidently find the end. The representation means that there is no real limit to how long a string can be, but programs have to scan one completely to determining its length. The physical storage required is one more location than the number of characters written between the quotes. The follow function string returns the length of a character string as, excluding the terminal \0. Be careful to distinguish between a character constant and a string that contains a single character. Single quote x is not the same as double quote x. The former is a single character used to produce the numeric value of the letter x in the machine's character set. The latter is a character string that contains one character, the letter x, and a \0. 2.4 Declarations. All variables must be declared before use, although certain declarations can be made implicitly by context. A declaration specifies a type and is followed by a list of one or more variables of that type, as in, variables can be distributed among declarations in any fashion. The list above could equally well be written as like this. This later form takes more room but is convenient for adding a command to each declaration or for subsequent modifications. Variables may also be initialized in their declaration, although there are some restrictions. If the name is followed by an equals sign and a constant, that serves as an initializer, as in like this. If the variable in question is external or static, the initialization is done once only. Conceptually, before the program starts executing, explicitly initialized automatic variables are initialized each time the function they are in is called. Automatic variables for which there is no explicit initializer have undefined hyponic garbage values. External and static variables are initialized to 0 by default, but it is good style to state the initialization anyway. We will discuss initialization further as new data types are introduced. 2.5 Arithmetic operators. The binary arithmetic operators are plus, minus, multiply, division, and the modulus operator percent. There is a unary minus but no unary plus. Once again, y. Integer division truncates any fractional part. The expression produces the remainder when x is divided by y, and thus 0 when y divides x exactly. For example, a year is a leap year if it is divisible by 4 but not by 100, except that years divisible by 400 are leap years. Therefore, the percent operator cannot be applied to float or double. The plus and minus operators have the same precedence, which is lower than the identical precedence of multiply, division, and percent, which are in turn lower than unary minus. Arithmetic operators group left to right. A table at the end of this chapter summarizes precedence and associativity for all operators. The order of evaluation is not specified for associative and commutative operators like multiply and plus. The compiler may rearrange a parenthesized computation involving one of these. Thus, a plus parenthesis b plus c can be evaluated as a plus parenthesis a plus b plus c. This rarely makes any difference, but if a particular order is required, explicit temporary variables must be used. The action taken on overflow or underflow depends on the machine at hand. 2.6 Relational and Logic Operators. The relational operators are greater than or equal, less than or equal. They all have the same precedence. Just below them in precedence are the equality operators, equal or and exclusive equal, which have the same precedence. Relational have lower precedence than arithmetic operators, so expressions like I less than lim minus 1 are taken as I less than parenthesis lim minus 1, as would be expected. More interesting are the logical connectivities, ampersand, and bar. Expressions connected by ampersand, and bar are evaluated left to right, and evaluation stops as soon as the truth or falsehood of the result is known. These properties are critical to writing programs that work. For example, here is a loop from the input function getLine, which we wrote in chapter 1. Clearly, before reading a new character, it is necessary to check that there is room to store it in the array S. So the test I less than lim minus 1 must be made first. Not only that, but if these test fails, we must not go on and read another character. Similarly, it would be unfortunate if C were tested against EOF before getChar was called. The call must occur before the character in C is tested. The precedence of ampersand is greater than that of bar, and both are lower than relational and equality operators. So expressions like this need no extra parentheses, but since the precedence of exclusive equal is higher than assignment, parentheses are needed to achieve the desired result. The unary negation operator exclusive converts a non-zero or true operand into 0, and a 0 or false operand into 1. A common use of exclusive is in constructions like if inward rather than if inward equals 0. It's hard to It is hard to generalize about which form is better. Constructions like exclusive inward read quite nicely, if not inward. But more complicated ones can be hard to understand. Exercise 2-1. Write a loop equivalent to the for loop above without using ampersand. 2.7 Type conversions. When operands of different types appear in expressions, they are converted to a common type according to a small number of rules. In general, the only conversions that happen automatically are those that make sense, such as converting an integer to floating point in an expression like f plus I. Expressions that don't make sense, like using float as a subscript, are disallowed. First, chars and ints may be freely intermixed in arithmetic expressions. Every char in an expression is automatically converted to an int. This permits considerable flexibility in certain kinds of character transformations. One is exemplified by the function a to I, which converts to a string of digits into its numeric equivalent, like this. As we discussed in Chapter 1, the expression gives the numeric value of the character stored in S bracket I because the values of 0, 1, etc. form a contiguous increasing positive sequence. Another example of char to int conversion is the function lower, which maps a single character to lowercase for the ASCII character set only. If the character is not an uppercase letter, lower returns it unchanged. This works for ASCII because corresponding uppercase and lowercase letters are a fixed distance apart as numeric values and each alphabet is contiguous. There is nothing but letters between A and Z. This later observation is not true of the ASCII character set. IBM 360/370 says this code fails on such systems. It converts more than letters. There is one subtle point about the conversion of characters to integers. The language does not specify whether variables of type char are signed or unsigned quantities when a char is converted to an int. Can it ever produce a negative integer? Unfortunately, this varies from machine to machine, reflecting differences in architecture. On some machines, PDP-11, for instance, a char whose leftmost bit is 1 will be converted to a negative integer, sign extension. On others, a char is promoted to an int by adding zeros at the left end and thus is always positive. The definition of C guarantees that any character in the machine's standard character set will never be negative. So these characters may be used freely in expressions as positive quantities, but arbitrary bit patterns stored in character variables may appear to be negative on some machines, yet positive on others. The most common occurrence of this situation is when the value -1 is used for EOF. Consider the code. On a machine which does not do sign extension, C is always positive because it is a char, yet EOF is negative. As a result, hang on. the test always fails. To avoid this, we have been careful to use int instead of char for any variable which holds a value returned by getChar. The real reason for using int instead of char is not related to any questions of possible sign extension. It is simply that getChar must return all possible characters so that it can be used to read arbitrary input, and in addition a distinct EOF value that thus its value cannot be represented as a char, but must instead be stored as an int. Another useful form of automatic type conversion is that relational expressions like a greater than j are logical expressions connected by ampersand, ampersand, and bar bar are defined to have value 1 if true and 0 if false. Thus, the assignment sets S digit to 1 if C is a digit and to 0 if not. If the test part of if, while, for, etc. are true, just means non-zero. Implicit arithmetic conversions work much as expected. In general, if an operator like plus or multiply, which takes two operands, a binary operator, has operands of different types, the lower type is promoted to the higher type before the operation proceeds. The result is of the higher type. More precisely, for each arithmetic operator, the following sequence of conversion rules is applied. Okay, these rules. Notice that all floats is an expression that are converted to double. All floating point arithmetic in C is done in double precision. Conversions take place across assignments. The value of the right side is converted to the type of the left, which is the type of the result. A character is converted to an integer, either by sign extension or not, as described above. The very first operation int to char is well behaved. Excess high-order bits are simply discarded. Thus, the value of C is unchanged. This is true whether or not sign extension is involved. If x is float and I is int, then x equal I and I equal s. Both cause conversions. Float to int causes truncation of any fractional part. Double is converted to float by rounding. Longer int are converted to shorter ones or to chars by dropping the excess high-order bits. Since a function argument is an expression, type conversions also take place when arguments are passed to functions. In particular, char and short become int and float becomes double. This is why we have declared function arguments to be int and double even when the function is called with char and float. Finally, explicit type conversions can be caused in any expression with a construct called a case. In the construction, the expression is converted to the named type by the conversion rules above. The precise meaning of a case is in fact as if expression were assigned to a variable of the specified type, which is then used in place of the whole construction. For example, the library routine sqrt expects a double argument and will produce nonsense if inadvertently handed something else. So if n is an integer, converts n to a double before passing it to sqrt. Note that the case produces the value of n in the proper type. The actual content of n is not altered. The cased operator has the same precedence as the other unary operators, as summarized in the table at the end of this chapter. Exercise 2 write the function h2i, which converts a string of hexadecimal digits into its equivalent integer value. The allowable digits are 0 to 9, A through F, and A through F. 2.8 Increment and decrement operators. C provides two unusual operators for incrementing and decrementing variables. The increment operators adds 1 to its operand. The decrement operators subtracts 1. We have frequently used to increment variables as in like this. The unusual aspect is that and minus may be used either as prefix operators before the variable, as in in, or postfix after the variable m++. In both cases, the effect is to increment m, but the expression n increments m before using its value, while m++ increments n after its value has been used. This means that in a context where the value is being used, not just the effect, n and n++ are different. If n is 5, then x equal n++, sets x to 5, but x equal n, sets x to 6. In both cases, n becomes 6. The increment and decrement operators can only be applied to variables. An expression like x equal parentheses I plus j plus is illegal. In a context where no value is wanted, just the incrementing effect as in. Choose prefix or postfix according to taste. But there are situations where one or the other is specifically called for. For instance, consider the function squeeze, which removes all occurrences of the character C from the string S. Each time a long C occurs, it is copied into the current J position, and only then is J incremented to be ready for the next character. This is exactly equivalent to this. Another example of a similar construction comes from the getLine function, which we wrote in chapter 1, where we can replace but more compact. In the third example, the function struct concatenates the string t to the end of the string s. Struct assumes that there is enough space in S to hold the combination. As each character is copied from T to S, the postfix ++ is applied to both I and J to make sure that they are in position for the next pass through the loop. Exercise 2 3 Write an alternate version of squeeze, which deletes each character in S1, which matches any character in the string S2. Exercise 2, middle score 4. Write the function any, which returns the first location in this string S1 where any character from the string S2 occurs, or -1 if S1 contains no characters from S2. 2.2 line. Bitwise logical operators. C provides a number of operators for bit manipulation. This may not be applied to float or double. The bitwise AND operator ampersand is often used to mask off some set of bits, for example, sets to 0 or but the low order 7 bits of M. The bitwise OR operator bar is used to turn bits on. Set to 1 in X, the bits that are set to 1 in mask. You should carefully distinguish the bitwise operators ampersand and bar from the logical connectivities ampersand and bar, which imply left-to-right evaluation of a truth value. For example, if X is 1 and Y is 2, then X ampersand 1 is 0, while X ampersand Y is 1. Why? The shift operators, left shift and right shift, perform left and right shifts of their left operand by the number of bit positions given by the right operand. Thus, X left shift 2 shifts X left by 2 positions, filling vacated bits with 0. This is equivalent to manipulation by 4. Right shifting and assigned quantity fills vacated bits with 0. Right shifting assigned quantity will fill with signed bits. Arithmetic shift on some machines such as the PDP-11, and with 0 bits logic shift on others. The unary operator yields the ones complement of an integer. That is, it converts each 1 bit into a 0 bit and vice versa. This operator typically finds use in expressions like which masks the last 6 bits of X to 0. Note that X ampersand yield 077 is independent of word length and is thus preferable to, for example, X ampersand 01777700, which assumes that X is a 16-bit quantity. The portable form involves no extra cost, since yield 077 is a constant expression and thus evaluated at compile time. To illustrate the use of some of the bit operators, consider the function getBits, which returns right adjusted the m-bit field of X that begins at position P. We assume that bit position 0 is at the right and that N and P are sensible positive values. For example, getBits returns the 3 bits in bit positions 4, 3, and 2, right adjusted. X right shift p plus 1 minus n moves the desired field to the right end of the word. Declaring the argument x to be unsigned ensures that when it is right-shifted, vacated bits will be filled with zeros, not signed bits, regardless of the machine the program is running on. Yield 0 is all 1 bit, shifting its left n bit positions with yield 0. Left shift n creates a mask with zeros in the rightmost n bits and ones everywhere else. Complementing that with yield makes a mask with ones in the rightmost n bits. Exercise 2.5 modify get bits to number bits from left to right. Exercise 2, middle score 6. Write a function word length which computes the word length of the host machine, that is the number of bits in an int. The function should be portable, in the sense that the same source code works on all machines. Exercise 2, middle score 7. Write the function right root which rotates the integer n to the right by bit positions. Exercise 2, middle score 8. Write the function invert, which inverts i.e changes 1 to 0 and vice versa. The n bits of x that begin at position p, leaving the others unchanged. 2.10 Assignment operators and expressions. Expressions such as I equal I plus 2, in which the left-hand side is repeated on the right, can be written in the compressed form using an assignment operator like plus equal. Most binary operators like plus, which have a left and right operand, have a corresponding assignment operator OP, where OP is one of, if E1 and E2 are expressions, then E1 OP equal E2 is equivalent to E1 equal parenthesis E1 OP parenthesis E2, except that E1 is computed only once. Notice the parentheses around E2. X multiply equal Y plus 1 is actually X equal X multiply parenthesis Y plus 1, rather than X equal X multiply Y plus 1. As an example, the function bit count counts the number of 1 bit in its integer argument. Quite apart from conciseness, assignment operators have the advantage that they correspond better to the way people think. We say add 2 to I, or increment I by 2, not take I add 2. Then put the result back in I. Thus I plus equal to. In addition, for a complicated expression like this, the assignment operator makes the code easier to understand, since the reader doesn't have to check painstakingly that two long expressions are indeed the same, or to wonder why they're not. And an assignment operator may even help the compiler to produce more efficient code. We have already used the fact that the assignment statement has a value and can occur in expressions. The most common example is Assignments using the other assignment operators can also occur in expressions, although it is a less frequent occurrences. It is a less frequent occurrence. The type of an assignment expression is the type of its left operand. Exercise 2 mid-score line. In a 2's complement number system, x ampersand parenthesis x minus 1 deletes the rightmost 1 bit in xy. Use this observation to write a faster version of bit count. 2.11 Conditional expressions. The statements like this, of course, compute in the maximum of A and B. The conditional expression written with the ternary operator question provides an alternate way to write these and similar constructions in the expression. Okay. It is time for me to take a break. Okay, see you guys later. Goodbye.